Okay, welcome back to ResEcon 313. These two classes are the second half of chapter 11. Okay, so in these two classes, the mathematics stuff is going to get even more intense. So feel free to pause this video at any point if you want to slow down to look at the mathematical stuff closely. Okay, so in the first two classes of this chapter, we looked at what is delta property. And when a person has delta property, we're referring to that person as a delta person. Okay. After we learned what is a delta person, we looked at how we can value perfect information for a delta person in any specific decision situation. And then we have also learned that a risk-neutral person is a special type of delta person. Okay, so we did a very quick look on that property in the last recording. And then we also defined the value of perfect information for a delta person as the difference between the value of a decision with free perfect information minus the value of that decision without perfect information. And that formula, the taking difference approach, only works for a delta person. It doesn't work for a non-delta person. Okay, so starting from this class, we're going to look at how we can use a utility function to represent a delta person's U-curve. So now we're switching gear from reading that U values from the U curves. We're switching into another method, which is we give a functional form of that U curve, and then we'll use mathematical way to find the U value of any uncertain deal for delta person. And we're particularly interested in, for all the delta persons in the world, do they share some similarities when we're looking at their utility functions? And the answer is yes, as we will reveal very soon. Okay. Just as a recap, so this binary relationship, this equivalent relationship, has been our focus for the majority of our classes in the semester. So what we are interested in is that if we're given any uncertain deals like this, where you have P1 probability of winning X1, P2 probability of winning X2, and P3 probability of winning X3. Okay, and if we're given such an uncertain deal, what we're interested in is to compare this uncertain deal to another one. Okay, we're trying to compare uncertain deals for a specific person. The way to do that is to compare the U values of different uncertain deals for a person. And we can do better than that. In addition to compare the U values of uncertain deals for a person, we can also find the certainty equivalent for all the uncertain deals for this person. And then whichever deal has the highest certainty equivalent is the most preferred deal. Okay. The reason is the reason that we can't just look at different uncertain deals and make a quick judgment without the help of U values is because, well, uncertainties are involved. You have to factor in people's uncertain preferences under uncertain situations. So for example, if you're looking at these three uncertain deals for a person, you can quickly judge which one is the most preferred, right? Well, you start with this one, have chance winning $1,000 and $0. Then if you look at the second deal, yes, you have a higher chance of winning now $0. However, the dollar amount is 800, lower than 1,000. So looking at these two deals, you can't really tell which one is more preferred by a specific person without really looking at his or her U curves. Similarly, if you look at the third uncertain deal here, yes, you have a higher price, $1,200. However, the probability of that getting that higher price is lower. So if you want to compare these three uncertain deals for yourself or other people that you care about or you're consulting for, then you really need their yield curve in order to make comparisons. And like I said, in order to choose or rank these three uncertain deals, you would need to either get their U values, the U value of this uncertain deal, the U value of this uncertain deal, the U value of this uncertain deal, and then rank these three uncertain deals based on their U values. Or you can get the certainty equivalent of this uncertain deal, get the certainty equivalent for this uncertain deal, get the certainty equivalent for this uncertain deal, and then compare the certainty equivalents of these three uncertain deals, and then rank them based on the rank of certainty equivalent. Okay, so that is what we mean by this X tilde sign over here. X tilde is the amount of money that, if received for sure, that gives you the same U value as the uncertain deal that it is equivalent to. Okay. So we're very interested in finding the certainty equivalent for an uncertain deal because we can use that to compare different uncertain deals. And we're interested in the certainty equivalent in addition to the U values of the deal is because sometimes we do need this certainty equivalent in order to make, in order to value perfect information as we did in the first two classes of this chapter. Remember, if we want to value perfect information, we need to find the certainty equivalent of the decision with and without perfect information, right? So that's how we put a dollar value to the as the value of perfect information by finding out the certainty equivalents of the decision scenarios. So just one line summary is that we are interested in finding certainty equivalents for uncertain deals within this class. Okay, so the next question that we've learned so far is how, okay? We want to find the certainty equivalent. How do we find that? Well, the way to do that is to first find the U values of the uncertain deals over here. Any uncertain deal that you're interested in, you need to find the U values of it. The way to find that is to use the probability of the first price to time it with the U value of the first price. Then add to it the probability of the second price times the U value of the second price. And then if you have a third price, that will be plus the probability of the third price, P3, times the U value of the third price times U of X3. Okay. So that's how we find the U value of this uncertain deal. And by definition, the certainty equivalent has also a U value, right? A certainty equivalent is a dollar amount. Then you can also find the U value of this dollar amount. That is what is marked over here. And these two should be equivalent, which means the U value of the certainty equivalent should be equal to the U value of the uncertain deal. This is just another way to state the definition of certainty equivalent. The dollar amount that gives you the same U value as would the uncertain deal will give you. Okay. So this equation gives you the value of the certainty equivalent. And so far, we have been dealing with this a lot, right? Through practices and in a lot of places. And the way we have been doing this is to use the U curve. So suppose we're interested in x1 equal to 100, then we would find x1 in 100 and then go up to the U curve and then go left to find the U value of $100. Okay, and then similarly, let's say x2 is equal to $50. We would go to this $50, go up to the U curve, go left to the U value axis to find the U value of the second prize, $50. And then P1, P2 is given in the uncertain deal. Then you would sum it up to find the U value of the uncertain deal. And then you would find that U value over here, then go right to the U curve and then go down to find that certainty equivalent, which is X tilde here. Okay, so starting this class, we're looking at a different way to find U values. So what if instead of representing a person's U value with such a graph, where you need to look up and down and constantly and then guess what is the dollar amount here, what is the U value here. What if you are given a function to represent this curve, right? As you may learn from your elementary algebra, this graph, there is a function behind it. So let's call it U of X. So in this class, we're looking at what kind of function we can use to represent a person's U curve. Specifically, what we're most interested in is, well, if this U curve over here is a Deltaperson's U curve, then what would the U function behind it look like? Do the Deltapersons share some similarities in their U functions? Okay, so again, we're looking at the U function in this class. Okay. Before we answer this question, what is a Deltaperson's U function looks like, utility function looks like, I want to bring your attention to the meaning of this x-axis over here. So remember, we got Kim's U curve, like over here, by asking her a lot of questions. What is your preference probability in binary deals between $0 and $100? So these are sort of based on the fact that we're assuming that Kim doesn't have any wealth at this point. Okay, he doesn't have any amount of money other than the party that she is about to look. So, but in reality, a person is rarely wealthless. Okay, so when we are looking at a person's U curve, what is on the left point of this horizontal axis is essentially what the person started, what the person started this decision situation with, right? So starting at the start, before I decide on a certain scenario, I have W0 amount of money in my bank. And then after I go through the deal, my wealth may be increased or decreased. So let's say if my wealth is increased, my wealth may further increase to what is we call W. Okay. The difference between W and W0 is the range of prizes or the range of uncertainty that you are facing in this uncertain deal. So this is the popular interpretation of the U curves. We're typically interpreting the U values as the U values of a person on the total wealth that belongs to her. And then these dollar amounts represent your current wealth at the starting point, and then add any amount that can be contributed by a decision situation. Then you get this total wealth situation. You started with W0, then you're facing an uncertain deal that may give you $0 or $100. Then at the end of the day, you're either walking away with W0 plus 0 or W0 plus 100. So that is the total wealth that you will walk away with at the end of the day. So here's an example. Suppose you have $1,000 to begin with. That is what you own before a certain decision situation. And then now you're facing a half chance of lottery between $100 and $0. In this case, W0 is referring to your initial wealth, the wealth that you started with before you played this lottery. That is $1,000. And here, X is the amount added. X could be $100 and $0, depending on which one you win. So if you do win $100, then at the end of the day, W would be equal to $1,000 plus $100. And if you win $0, then W that the wealth that you end up with is just $1,000 plus 0. So over here, instead of putting 0 or 100 at the horizontal axis, we are going to add the initial wealth to these prices. So over here, this would be $1,000, and this would be $1,000 and $100. Okay. So this is how we typically draw the yield curve. That is by incorporating the wealth that a person has before a certain decision situation. Okay. With this being said, meaning that when we're looking at yield curves, we're considering the sum of the initial wealth with the different increment or decrement of wealth levels due to an uncertain deal. We need to incorporate that into our search for the U function as well, right? In the utility function, we should also, the argument, the input of the utility function should also be the sum of your total wealth, meaning your W0 plus your prices. Okay, so keep that in mind. This is why we're going to, this is the type of yield curve we're going to use going forward. So over here, now we're finally ready to go ahead and take a look at a person's utility function given this new interpretation of the x-axis. Okay, so the first thing to notice is that this is what we're referring to when we're looking at the delta property, right? So initially, this uncertain deal has a certain equivalent of x tilde. If we add delta dollars to all the prices of the uncertain deal, then the certainty equivalent should go through the same amount of change. Okay, so this is the definition of a Deltaperson. Okay, so how do we define the property of a Deltaperson using these U functions, utility function? Okay, so if you look at this deal over here, like what we saw before, there is an equivalent relationship. So that means the U value of this should be equal to the U value of this uncertain deal. Okay, now this is the U value of the certainty equivalent. So here W0 is added to reflect what we just saw in the previous slide. We need to interpret these values by adding up the initial wealth to it. Okay. And then the U values of this uncertain deal is either you get W0 plus X1 plus delta, or you get W0 plus X2 plus delta, or you get W0 plus X3 plus delta. So that is what is reflected over here. So I is a sort of a constant that can take value of 1 or 2 or 3. So you have W0 plus X1 if I is equal to 1 plus delta times P1. And this is just a summation sign that tells you that you're summing this term over all the i's when I is equal to 1 or 2 or 3. So to expand this out, it would just be P1 times U of W0 plus X1 plus delta plus P2 times U of W0 plus X2 plus delta plus P3 times U of W0 plus X3 plus delta. Okay, so this equal sign is over here, the equivalent relationship. So this equation represents the relationship that we're seeing at over here. Okay, so now what kind of properties does this X tilde need to have in order for this person to be a Deltaperson? So that is when so when do we have a Deltaperson looking at this equation? Okay, so this is just the certainty equivalent of the uncertain deal after adding delta dollars and with an initial wealth of W0. So if this certainty equivalent, this delta X tilde amount is not changing, with either W0 or delta, then we have the delta property. Okay, think about this. You can put delta equal to 0. Then u W0 plus x tilde is equal to the sum of pi times u of W0 plus xi. That corresponds to this relationship, right? That gives you the x tilde of this relationship. Then adding delta, that gives you the x tilde of this relationship. Then if the x tilde from this one is not changing with the x tilde in this one, then we do have the delta property, right? If what is over here is changing after we add the delta values, then we don't have a Deltaperson. So to conclude, starting with this equation, and what we're interested is this x tilde. If x tilde, after you solve it mathematically, it does not depend on delta or W0 at all, then you have a Deltaperson, or you have a utility function that satisfies the delta property. Okay, so you can search for all the utility functions that has this property, that has this delta property. And at the end of the day, you will find only two types of utility functions that can satisfy this condition. The first type of utility function is called a straight line utility function, also referred to as the linear utility function. And the second type of function is the exponential utility function. Okay, we'll look at both of these, and we'll look at how do we apply both of these two types of utility functions, and starting with the straight line utility function. Okay, so what we're going to do now is to prove that a straight line utility function satisfies this property. We use this equation, apply that to a straight line utility function, we solve for x tilde, and at the end of the process, you will find that x tilde is not dependent on W0 or delta. Okay, so when we say a straight line utility function, we're referring to a utility function for a person like this. Okay, so the u values of any amount of money is equal to A plus B times that amount of money. So here, Y is essentially referring to the total wealth that you are facing in an uncertain deal. And here, A and B can represent any constant numbers. The value of A can go anywhere, but however, B has to be positive. So why? Why is that? That's because typically we would assume that more money has a higher U values. That is consistent with our 5 rules of actional thought, or just the common sense that more money is better. Okay, so that means B has to be positive, meaning when Y increases, when B is positive, then the U of Y will increase. If B is less than 0, then if Y increases, the U value of Y would decrease. That would correspond to the situation where more money brings less utility. Okay, that is not a valid utility function. Okay, so this is the linear utility function we're referring to. For example, A could be 0, B could be 1, A could be 10, B could be 100. So any of those any values of A and B, as long as B is positive, is a straight line utility function. So what we're interested to do, like I said, is to check whether this utility function satisfies the delta property. To do that, we need to sort of use this U function to write out this equation, right? Utility of certain equivalent is equal to the U value of an uncertain deal. So after we write this equation by substituting this straight line utility function in here, then we'll solve for x tilde. If x tilde is not changing with W0 or delta, we have a Deltaperson. So let's do the first step. Use this function, substitute this into this function. meaning instead of using u of this, we're using this expression of u to represent this equation. So here on the left-hand side of the equation, the y here would be equal to W0 plus x tilde plus delta. Okay, so that's how we got this expression. A plus B times the amount of dollar final wealth. Okay, and then over here, we would have the sum of PI times the U values of each price, which is A plus B times each price added by the total wealth. Okay. So let's carry this equation to the top of the next page. Nothing changed from here to here. And then we can simplify both sides of this equation by multiplying the B, by multiplying each term in the parentheses out with the multiplier B. Okay, that's how we have over here on the left-hand side of the equation, A plus B times W0 plus B times x tilde plus B times delta. And then over here, we would multiply out each one of these terms. And then also we can just group up the same terms. So over here, you have the sum of PI times A, the sum of PI times B times W0, that is the BW0, and then further multiply out with PI. And then PI times B times XI, and this term. Okay. And notice that we have already said that when we have an uncertain deal, all the probabilities need to add up to 1. Okay. So that means this term is equal to A, this term is equal to B times W0 because this term is equal to 1. And this term is equal to, we cannot do this term because there's this xi term that is changing with respect to I. So all that we can do is to pull the B out and then group the changing part together. And then here we do have the sum of PI equal to 1, then we have B delta. And then we can simplify it by crossing out the equal terms on the two sides of the equation. So here A is crossed out because they are on both sides. And then B times W0 can be crossed out. And then this B times delta term can be crossed out. Okay. And then the B, the multiplier B, is on both sides as well. So after we divide both sides by B, we end up with this. We end up with this x tilde term equal to this term, the sum of PI times XI. If you think about this, the sum of PI XI, it is just the expected value of an uncertain deal, right? So by solving for x tilde, we have figured out that if we start with a straight line utility function like this, the certainty equivalent would be equal to the expected value. Okay, by definition, that is what we call a risk-neutral person. Okay, so as it turns out, a straight line utility function actually represents the utility function of a risk-neutral person. Okay, that's the first observation. The second observation is that when we solve for this x tilde, at the end of the process, this expression doesn't have W0 in it, which means x tilde is not changing with respect to W0. And this term doesn't have the delta term in it either, which means x tilde is not changing if delta changes. This is the property that we're looking for when we are looking at a delta property, meaning a straight line utility function will satisfy the delta property. That is also consistent with what we learned before, that a risk-neutral person is a delta person. Okay, so we have two conclusions actually from the process of solving for x tilde. First, straight line utility function represent a person who has delta property. Second, Straight line utility function represent a person whose certainty equivalent is equal to expected value. That is the definition of a risk-neutral person. Further making the connection between these two observations, we again have proved that a risk-neutral person is a delta person. Okay, so this is just the summary. Straight line utility function represent a risk-neutral person. If a person is risk-neutral, then her utility function must be the straight line utility function. It cannot be of any other forms. And again, a risk-neutral person is a delta person who values uncertain deals at the expected value. Okay, so this is the first type of utility functions that satisfy delta property. The second type of utility functions that satisfy delta property is called the exponential utility function. So instead of the uy equal to a plus b times y, it takes this form, okay? So u of y is equal to a minus b times another constant number over here, raised to the power of negative y. Okay, here a and b and r are constant numbers that are changing from one person to another. What doesn't change is this form, that a is minus p times r raised to the negative of y power, and this y is the total wealth that you're facing in a decision situation. Okay, so we need to have, again, the u values of the money amount should be increased when the money amount increases. So that is why only one of the three cases are allowed. So when r is less than 1, b has to be less than 0. This corresponds to a risk-loving delta person. When r is greater than 1, b has to be positive. This corresponds to a risk-averse delta person. You may notice that when r is equal to 1, then number 1 raised to any power is 1. So in that sense, the r1 raised to the power of negative y is equal to 1. So this utility function becomes a minus b. It doesn't make any sense. Y is not in here anymore. So we don't allow r to be equal to 1. As a matter of fact, when r is equal to 1, we would use the linear utility function that we looked at instead, because r equal to 1 corresponds to the risk-neutral situation. Okay, so over here for this exponential utility function, we're no longer going through the proving process as we did for the linear utility function. We did that for the linear utility function just to give you a flavor of how to prove it. The mathematics to prove this utility function satisfies delta property is much too complicated and not really interested in our class. We're not really interested in that. So we're skipping that part. And I'm just giving you the conclusion that this utility function does satisfy delta property. And these are the two cases that could arise from this utility function, given different values of r and b. Okay. Again, when r is less than 1, then b need to be less than 1 to ensure that the u values are increasing when y increases. And when r is greater than 1, b has to be positive in order to ensure that the u values of the money is increasing when the money amount increases. Okay. I'm also skipping on the reasoning of that, but it is not super hard for you to figure it out when a function is increasing or decreasing with respect to its input, something you should have learned in your algebra classes. If you're interested, we can go through that in our office hours, but not during the class. So here is an example of one utility function that satisfies this exponential utility function form. So over here, suppose that we have someone called Alice, and whose utility function takes this equation. So over here, if you compare this example with the exponential utility function, the general form of it over here, then A would be equal to 1, which is over here. B is also equal to 1. Since you are using 1 to multiply this term, it is just, we don't write 1 times 1.5 over here. And then R is equal to 1.5, and then it is raised to the negative of y. So this is one utility function that takes the exponential utility function form. And as you can see, R is equal to 1.5. That corresponds to a risk-averse Deltaperson. And this blue line is the graph of this utility function. So this, echoes my point at the beginning of this class that the yield curves, there is a utility function behind it. The graph of this utility function is the yield curve of Alice. Okay, before we're focusing using this curve, now we're interested in using this function, this mathematical representation of this curve. And something we mentioned before, whenever a yield curve bows upward, we have a risk-averse person. That is consistent with the fact that when R is equal to 1.5, which is greater than 1, then we have a risk-averse person. Well, let's suppose we are looking at another person, maybe called Bob, whose utility function has an R of 0.5, which corresponds to this case. Then the yield curve for Bob would look like this. It would be bowing downward, which corresponds to a risk-loving person. Okay, so these two conclusions are sort of given to you without the process of proving it. That is not very important at this point, and knowing the conclusions is good enough for this class. Okay, so this completes our answer to the first question we're interested in. What is a Deltaperson's utility function look like? Okay, and the answer is a Deltaperson's utility function can only take one of the following two forms. It can either be a straight line utility function, which means we have a risk-neutral person, or it could take the form of the exponential utility function like this. And then when R is less than 1, B less than 0, and this case corresponds to the risk-averse Deltaperson. Notice here, from solving x delta using the straight line utility function, we get to the conclusion that a straight line utility function represents a risk-neutral person. Here we don't have an x delta equal to something over here because it's just too complicated of a expression, and we're really not interested in that. Instead, we're going to use another property of the exponential utility function to characterize a person's risk attitude when her utility function takes this form. That is the next topic of the class, of the chapter, namely the risk odds of a Deltaperson. Okay, so going forward, we're especially interested in the exponential utility function, or any people with an exponential utility function. And specifically, let's start looking at a risk-averse person whose utility function is like this, meaning we're looking at a risk-averse Deltaperson who will definitely have a utility function like this. And further, in order for this person to be risk-averse, R has to be greater than 1, B has to be positive. So we're focusing on such a type of utility function that takes this form, and further, when R is greater than 1, B is greater than 0. As it turns out, all that matters in this utility function is this R parameter. And this R parameter represents the risk odds of a risk-averse delta person. I'm going to interpret to define what are risk odds one step at a time, and then you see this conclusion at the end of this section of lecture. Okay. So before we introduce the concept of risk odds, I want you to recall what is the odds of a binary deal. Okay, so this is something we learned very early on in this semester. So if you have a binary deal, again, if you have a deal with 3 prices, you can't use the odds ratio to characterize that deal. However, if you have a deal that has only 2 prices, then the ratio of the 2 prices probabilities is called the odds ratio of that uncertain deal, right? So over here, you're looking at a special form of binary deal that has the same stake, but either winning it or losing it. Okay, so this represents a binary deal of winning or losing $1. Or you could describe this binary deal as a binary deal with $1 at stake. At stake meaning you're losing or you're winning or losing that stake. Okay, over here, as you read this uncertain deal, you would obviously winning $1 has the probability of P, and losing $1 has the probability of 1 minus P. They have to add up to 1. That is why one is P and the other is 1 minus P. So P could take the value of 0.5 or 0.2, then 1 minus P would be 0.5 or 0.8. And then over here, we say that the odds of winning $1 in this binary deal is the probability of winning $1 divided by the probability of losing $1. Okay, so this is consistent with what we call the odds ratio in a binary deal. Okay, odds of winning something, the probability of that goes to the top, and the other one, the probability of the other possibility goes to the bottom. Okay. As you can see, when you have a higher probability of winning $1, meaning when P is higher, then this odds will be higher as well, right? So a higher P corresponds to a higher odds, which is something that you would prefer, right? You would prefer to have between 2 uncertain deals of winning or losing $1. You would prefer the one that has a higher probability of winning, which is consistent, equivalent to preferring a binary deal with a higher odds of winning. Higher probability of winning $1 is equivalent to higher odds of winning $1. Just saying, from these points, I'm just conveying a simple observation that when the odds of winning is higher, in any binary deals, you would prefer that situation. Okay. You would prefer a deal with higher odds of winning $1. This is just what the choice rule told us. Okay. Also, we learned something called preference probabilities before, right? So now what we're interested in is a special type of preference probability that makes you indifferent between taking a deal like that like what we just saw, and not taking the deal. Okay, so we're interested in a P that makes you indifferent between taking this deal and not taking that deal. Okay, whenever we say indifferent, that involves 2 options, taking the deal or not taking the deal. Okay, what would not taking the deal entail? Okay, so if you do not take the deal, meaning you're not winning or losing a dollar, meaning you're just getting $0 for that situation. Okay, and if you take the deal, then you have an odds of winning a dollar, which is equal to P, or over 1 minus P. So for this $0, if you are indifferent between not taking and taking the deal, what kind of P makes this indifference sign hold? Okay, that is essentially asking you, well, what is your preference probability of $0 in a binary deal where you could win or lose a dollar? Okay, just connect what we're asking here with the term preference probability that we learned before. Preference probability refers to the probability of the higher price that makes you indifferent with a certain amount of money. So here P would be the preference probability of $0 when we are looking at a binary deal between a dollar and losing a dollar, winning and losing a dollar. Okay. And since we have some amount over here that is between 1 and -1, by the equivalence rule, we should be able to state a P over here, right? Remember, when we look at the equivalence rule, it tells us that for a certain amount of money that is between the two prices in an uncertain deal, you will be able to state a preference probability that makes you equivalent between the two options. Okay. So this preference probability lead to an odds, right? So if you have a P over here, then you would have an odds that you can calculate based on your preference probability. That odds is referred to as risk odds. Okay. Well, suppose you are a person who has a P of 0.5, then we say that your risk odds in this binary deal is 0.5 over 1 minus 0.5, which is 1. Okay. So risk odds correspond or we're referring to the odds that corresponds to the preference probability. Okay, I want you to look at this definition of risk odds long and carefully. Risk odds has in it an equivalent relationship. Okay, it is referring to the specific odds that corresponds to the indifference probabilities. Okay. So what we're interested in now is what is the risk odds? We are interested in what are the risk odds or what are the preference probabilities in a binary deal like this for a Deltaperson. Okay, so let's start with looking at what is the preference probability for a Deltaperson in a binary deal between winning and losing $1. Okay, so since we're looking at a Deltaperson, let's pull up her utility function over here. And we're interested in what P makes a Deltaperson indifferent between taking this binary deal and not taking this binary deal. So we're solving for P using this equivalent relationship. Okay. So when we're trying to solve for P, we need to represent the left-hand side and then represent the right-hand side, the U values of both sides, and make it equal. So what we need to do is to find the U value of no deal and then the U value of this deal. So the U value of no deal is just the U value of 0, okay? So let's put 0 into this function that gives us the U value of 0. And then the U value of this binary deal is P times the U value of 1 plus 1 minus P times the U value of -1. Okay. And then this is just the definition or the equation without substituting in the utility function. Now let's just plug this 0 into the position of y. That gives us a minus p times r raised to the power of negative 0, which is just 0. So this is the plug-in value of this when we plug the 0 into the position of y. Similarly, let's plug the value of 1 into the position of y. That gives us this value, a minus b times r raised to the power of negative y. Here y is 1. Okay, so that this expression corresponds u value of 1. And then plus 1 minus p times u value of negative 1. So let's plug the negative 1 over here to the position of y. So this is how we got. So now we have an equation with only a, b, r's, and then p and 1 minus p. Okay, if you look at it, everything is known except for p. We're assuming we know this person's a, b, and r. Then we can sort of solve this equation for the expression of p. Again, I'm skipping the process of solving this equation. The textbook has it if you're interested. Here, I'm only giving you the conclusion. When we solve for p out of this equation, we will have p is equal to r over 1 plus r. As you can see, when we simplify this equation and solve for p, we do not have a or b in this expression, in this solution for p. P, the only parameter, the only constant numbers out of a, b, r that matters for p, for the preference probability, is r. And specifically, p will be equal to r over 1 plus r. Okay, something very important for you to remember. And the values of a and b does not matter in the preference probability in this binary relationship. Okay, here's an example again using Alice that we saw, who has a u function, a utility function like this. Again, I have pointed out to you that this utility function corresponds to a equal to 1, b equal to 1, and r equal to 1.5. Then we would know Alex will be indifferent between not taking the deal and taking the deal of winning or losing $1 if the odds is 1.5 over 1 plus 1.5, which is equal to 0.6. This is just a plug-in of this expression for the solution of p. Okay, you don't need to solve for p every time. You can use this formula, use this expression to find the indifference probability, the preference probability of a person. And as you can imagine, if we have another person whose r is equal to 2, then this p would be equal to 2 over 1 plus 2, which would be equal to 1/3. Okay. So this probability 0.6 is the indifference probability, meaning when p is equal to 0.5, Alice is indifferent between this binary deal and not taking the binary deal and walk away with $0 losing or winning. Okay. Now, as you can see, what if the binary deal is offered to Alice with a p with the probability of winning $1 higher than 0.6? Then Alice would take it. Okay. If Alice is offered with a binary deal of winning or losing $1 when p is less than 0.6, then Alice prefers not to take it and walk away scot-free. Okay. So as we have defined before, the odds, the risk odds of a delta person is just the ratio between the preference probability and 1 minus the preference probability, meaning the odds, the risk odds of a person is just P over 1 minus P. Okay, so let's take a look at that. So when you have this equation, you can find P, which is equal to R over 1 plus R. Let's look at it over here. So the risk odds is equal to P over 1 minus P. And we have already learned that P is equal to this R over 1 plus R. So let's put that in. And 1 minus P is equal to 1 minus R over, sorry. This is because P is equal to this term. And then after you simplify this expression, you will have, you can multiply the numerator and the denominator both by 1 plus R. Then on the numerator, you would get R. On the denominator, you would have 1 plus R minus R. And these two cancels out, and then you end up with R. So as it turns out, risk odds of a delta person is equal to the R parameter. Okay. The risk odds, P over 1 minus P, we know P is equal to R over 1 plus R. Then substitute in, like I illustrated, you will have the risk odds of a delta person. So R is the risk odds for winning or losing $1. So that's how we use the term risk odds in a sentence to describe a certain situation. So R is essentially when we have $1 at stake, R is the odds of winning that makes one person indifferent between taking the deal and not taking the deal. Okay, and of course, if the odds of winning is higher than R, which means the probability of winning is higher than P, then a person would take it. So here another example. Again, we're looking at Alice, and then we know Alice will be indifferent between taking a deal or not taking a deal when the odds of winning $1 is just this R. If Alice is offered a deal with a higher odds of winning $1, she take it. Whenever we say risk odds, we're referring to that indifference odds, okay? And whenever we do not have this risk term before the odds term, we're describing something objective of a certain deal. So keep in mind that whenever we have the word risk before odds, we are referring to a specific odds that makes one person indifferent between taking a bet with a stake or not taking the deal. So this is what we have done so far. We are specifically interested in a binary deal of winning $1 or losing $1. We're looking at a binary deal with $1 at stake, and we're interested in the P that makes a delta person indifferent between taking that deal and not taking that deal. And then if we figure out the P, we can figure out the odds of that indifference deal, which is what we refer to as the risk odds. Everything we're talking about so far is specific to a stake of 1. Now, what if we're looking at another deal that has a stake of not $1, let's call it M dollars. M could be 2, 3, 4, 5, 10, a million, no, it doesn't matter. We're referring to a stake. We're referring to a binary deal with a stake other than $1. And we are also interested in the preference probability that makes a delta person, a risk-averse delta person, indifferent between taking that deal and not taking that deal. So this is exactly the same format as before, except that the stake at hand is no longer $1, it's M dollars instead. And we're using kill rather than P to remind ourselves that this preference probability could be different from the previous preference probability for $1 situation. And we're interested in finding this Q, the preference probability of $0 in the binary deal with M dollars at stake. Okay. So we go through the same process as we did before for solving P, the preference probability for $1. So we go through that again. Over here, U of 0 over here, U of M is just by plugging in M to this utility function, and U of negative M is just plugging the negative M term to Y, which gives you this expression. And we're looking at an indifference relationship. We need to make this equal to the U value of this, which means A minus B, the U value of 0, is equal to, now we're looking at Q. Q times the U value of M plus Y minus Q times the U value of negative M. And then again, we have an equation where there are A, B, R's, and then there is a Q. So obviously you can solve for Q, and again, we're escaping that process. You will find that Q is equal to this expression. Again, if you look at this solution, this formula for Q, and recall the formula for P, when we look at P, we don't have this M term because we're looking at a $1 stake. Well, actually, if you make M equal to 1, then the Q is the same with the P. That means P is a special case of Q when M is equal to 1. Okay. So applying this formula to a specific example, again, we're looking at Alice, who is a risk-averse Deltaperson who has an R of 1.5 in her utility function. Now we're interested in what kind of a probability of winning would make Alice indifferent between not taking and taking a deal where the price is either $5 or negative $5. And then we just plug in this. We just use this formula to look for that probability. Since we're looking at a binary deal of winning or losing $5, meaning the stake is $5. That means R raised to the power of 5 over 1 plus the R value raised to the power of 5. And if you use your calculator, that corresponds to 88%, okay, 0.88. Similarly, this Q only is the preference probability when M is at stake. Then the odds is just Q over 1 minus Q. You can do this, you can plug in Q equal to this term into this expression and simplify it. You will find it is equal to R to the power of M. So the risk odds for winning or losing M dollars is the R parameter raised to the stake. Again, Alice's risk odds for $5 would be equal to her R, which is 1.5, raised to the power of 5, which is equal to 7.59. And she'll take a deal with $5 at stake as long as the odds of winning is over 7.59. This is exactly the same with this, only that using this expression, we're focusing on the preference probability. And using this expression, we're focusing the odds. So just a recap of what we have learned so far. For binary deals with either $1 or M dollars at stake, this is what we learned. If we have a $1 stake, or if we're looking at a binary deal between of winning or losing $1, and if we have someone called a Deltaperson who has this utility function, then the odds, the risk odds for that person in the binary deal is equal to R. However, if we look at another binary deal of winning or losing M dollars, or when M dollars are at stake, then the risk odds of this Deltaperson is equal to R raised to the power of M. So as it turns out, there is a relationship between the risk odds for $1 and the risk odds for M dollar, right? So R is equal to the risk odds of $1, so we can replace the R with P over 1 minus P. That means the risk odds of winning or losing M dollars is just the risk odds of winning or losing $1 raised to the power of M. Okay, so going forward, we're going to write this risk odds term using some kind of special notation, if you call it, if you will. So over here, we're using R parenthesis M to refer to the risk odds of winning or losing M dollars, which is essentially equal to Q over 1 minus Q. Okay, and then we're using R to refer to the risk odds of winning or losing $1. So using that notation system, we can rewrite this relationship as this. The risk odds of winning or losing M dollars is equal to the risk odds of winning or losing $1 raised to the power of M. Again, just another system of notations that we may use in the future. Okay. For any different amount of money, X or Y, the risk odds, we are using this formula now. We're using this expression and this formula now. Now, if M is equal to X, the risk odds of X dollar is R raised to the power of X, okay? That is what we have here. The risk odds for winning or losing X dollar is this. And the risk odds for winning or losing Y dollar is this. Just, the dollar amount, just raise the risk odds of winning or losing $1 to the other dollar amount. Now, as a matter of fact, you can make a connection between the risk odds of winning or losing X dollar with the risk odds of winning or losing Y dollar. If you are risk averse, if you are a Deltaperson, then you would have this relationship. Okay. So when Y is equal to 1, that is you are having that formula before. Okay, it's just a special case. The risk odds of winning X dollar is related to the risk of odds of winning Y dollar in such a way. The risk odds of X dollar is equal to the risk odds of Y dollar raised to the power of X over Y. Okay, just a relationship that we have for a Deltaperson. What does this help us? Now, if we know the risk odds of a Deltaperson for X dollars, then we can find the risk odds of this Deltaperson, the same Deltaperson, at any other stakes other than X, right? Using this formula. Here is an example. If we know Chris is a Deltaperson, and that we know Chris has a risk odds of 1.5 for a dollar amount of $100. Again, get comfortable with this expression. R of $100. The risk odds of $100 is 1.5. Now the first question is, what is Chris's preference probability of in a binary deal between losing or winning or losing $100? That is just the R over 1 plus R expression. Okay, so here the preference probability in the binary deal between losing or winning or losing X dollars is equal to the risk odds of X dollars over 1 plus the risk odds of X dollars. So using this formula, we could figure out Chris's risk preference probability in the binary deal. So we know that Chris will be indifferent between not taking the deal and getting $0 with the deal of winning $100 with 60% of the chance. Now the question is, what can we say about Chris's risk odds at $1,000? That is, what we are looking for is the risk odds for $1,000. Then we can just use the formula. The risk odds of $1,000 is equal to the risk odds of $100 raised to the power of the ratio between these two. We know that the risk odds of $100 is 0.5, then 1.5 is over here, and the 1,000 over 100 is just 10. So the risk odds for $1,000 is 57.67 for Chris. Now, what is the preference probability for $1,000? That is just, using this formula again, the risk odds over 1 plus the risk odds, which is 98.3%. Chris will be indifferent between receiving $0 for sure and a binary deal with probabilities of 0.983 of winning $1,000 and 0.017 of losing $1,000. As you can see, in order for Chris to take a deal that has a higher stake of $1,000, you will have to give him a deal of winning that is with the probability of winning higher than 98.3%. This is the probability that you're looking at when $1,000 is at stake. Versus here, for a deal with $100 at stake, as long as you give Chris that deal with a winning probability higher than 60%, Chris would take it. So the threshold for Chris to take a deal with $1,000 at stake is higher than the threshold for Chris to take a deal of $100 at stake. So that tells us that Chris is getting more and more cautious as the stake gets higher and higher. Okay, here's another example. Now we have Wendy, who is a Deltaperson with a risk odds of 2 for $100. And then you can figure out what is Wendy's preference probability for winning or losing $100. What is Wendy's risk odds for winning or losing $50 instead? And what is Wendy's preference probability for the $50 stake situation? You can pause here to work on this, and when you get the answer, I am now to reveal the answer to you. So here, the preference probability using this formula is the risk odds of $100 over 1 plus that, which is 0.66. Now the risk odds for winning or losing 50 is, we're using this formula, R of 50, the risk odds of $50 is equal to the risk odds of $100 raised to the power of the ratio between the two. That is the square root of 2, which is 1.41. Now the preference probability for winning or losing $50 is just 1 point. The risk odds for $50 over 1 plus that risk odds, which is 58.5. Okay, so this is the end of the lecture on risk odds and the utility function of a Deltaperson. So yes, a lot of mathematics over here. So you may need to watch this video twice at certain parts for you to fully understand. But this will be very handy for you to solve for problems for Deltaperson rather than using the U-curve, which takes a lot of guess in reading the numbers on the axis.